first 30 minutes of lecture is going to go over 110 content. First idea is you have an arbitrary network that has R, L's, C's, and transformers. These components guarantee linearity because they have linear response. With no independent sources within this network, you can abstract this network away as a transfer function. So some of you may know this is what we consider a basic case of a two-port. So it kind of looks like this. And this has some, h of t corresponds to some h of s because it's an LTI two-port. We can do this L because it's linear, because these components time invariant, and the no independent sources means that whatever we do to this, we have to externally excited, Antoine, to get a response out of it. So basically, we don't attach any excitations to this, any voltage sources externally or current sources externally, we're going to get a null output. So, if this has, I'm going to abstract the detail away. I'll be posting all these notes that have more detail. So, in reality, if you want, you can make this like a 3-port or like a 4-port, and so forth. For the context of graph, we care about stringing things together, right? One after the next after the next in a chain. So we like to deal with 2 ports. This kind of makes sense, right? When you saw your filters, it kind of looks like this, and you have an SMA connector here and an SMA connector here. 2 ports have 4 terminals. And you may ask, okay, well, there's 2 terminals here, right? For our filters, how does that make sense? We have a center conductor, which is our signal path for both, and the outer casing is our ground. So this is our ground. This is our ground. Similarly here, typically you'll have this be connected to ground, and this. And when you attach any external voltage source, it'll just be in reference to this ground here, right? So you kind of see how that applies. Any questions on that? Cool. So graph, we like 2 ports. We want to work with 2 ports, and when we string them together, we want to have a good understanding how they operate. So we can just say that V1 is being sent into this network, and we can measure a corresponding V2. Kind of straightforward. We have a closed loop here, so we're going to have some current here, and there's no current here. This kind of makes sense intuitively. Now, I said that we can model this as a transfer function, and when we talk about transfer functions, we have an input, multiplied by a transfer function, you get your output, right? If this is like a voltage divider, then we can get a transfer function from it, right? So, how could we take this 2-port, has these 4 terminals, and represent this in some mathematical notation that allows us to, do circuit manipulation? End of the day is you want to abstract away any complicated circuit into very simple parameters that we can just plug and chug, right? Whatever's inside here, no matter how many R's, L's, or C's, get a nice little equation for it and call it a day. So there's a few representations we can do. And let's just say, something that looks like this. Now, this is technically, I wouldn't say illegal, but when you talk about, what I had before is you put a V1, it's going to have an I1, and you can measure a corresponding V2. If you're trying to measure V2, that means you can't excite this port at the same time, right? Kind of, if you look back at what we did in the earlier modules where you're doing like an AC sim, you can't have an excitation at the same time at the input, you have to null it, right? So if you want to figure out the V2 with respect to whatever you're putting in over here, remove this voltage source, open it like that, and you can measure it. But generally speaking, you can attach voltage sources to both sides of it, and you can get corresponding currents as a result. So is there a way to capture this relationship of we have a voltage on each side that has a corresponding current going into this network? Is there a mathematical formulation here? And there is. We can just make a matrix. Right? This is your admittance basically, right? Your 1 over ohms is the unit of this. And Y can be represented like this. So basically, if if we know whatever current we're trying to put in, if we want to get a certain voltage out, or vice versa, if we know this matrix, we can do that conversion. How do we figure out this matrix? That's the tricky part. There's another representation we can do here, and this is called Y parameters. We can do impedance, which we're more familiar with. So we can do V1, V2 equal to Z11, Z12, Z21, Z22 times your I1, I2, just like that. This kind of makes sense, right? We're all good with this? Okay. Call these Z parameters. And effectively, again, we know this. All we have to do is just take our input signal, multiply, get our output. Now, I'm going to erase this. Okay, so let's say we want to figure out what V2 is. Write the equation for V2. Okay, this is going to be okay. Now let's say we want to figure out V2 as a result of a stimulus on this side. For us to do that, we have to disconnect this voltage source, which means this voltage is 0. Sorry, this current here is going to be 0. No current goes here, we're not going to have any voltage drop here, right? So if that current is 0, in order for us to get V2 in terms of whatever I1 is, I2 has to be 0. If that's the case, you get that V2, Z21, I1, for a voltage source here on the left. Any questions on that? Cool. Similarly, if we want to do V1, we can just do this. We can do Z11, I1 plus Z12, I2. And now we can say that we said I2 equal to 0 here. From before, get that V1 is equal to Z11, I1. And now we see that we can solve for I1. So I1 is going to be equal to V1 over there. Z11, if we plug that back in over here, get that V2 for V1 is going to be equal to, let's make my mental math here. Z21 over Z11. Now, V2 or V1, you can think of that as like the gain from here to here, right? So this is great. When we talk about putting these systems together, we talk about signal gain, signal loss, right? So we have a signal over here. We know Z21, we know Z11. We can figure out what V2 looks like. That's our gain. So it's kind of a handy number to remember, right? But calculating Z21 and Z11 is a little tricky. And these two core characterizations we've talked about, this Y and Z parameters, they don't easily apply to wrap. And I'll show you in a second why. The math is not as easy as you think it may be. I'll show you an example, a very simple example. I'm going to erase this bottom part here. Let's consider a simple voltage divider. Our two-port network here. This bottom is ground. This is V11. Okay. So let's do a few things here. Okay. Let's say we want to figure out what Z11 is. So for Z11, what we do is we say let's apply V11 is V1 over I1, given that I2 is 0. If I2 is 0, there's no current here, right? So this is good. This is open. That makes sense. Now we talk about V1 over I1. That is whatever impedance we see here. 0 and 1. If we look this way, right, no current goes here. So we apply any current here. It's going to go this way, go across, go down, do that loop. So that impedance is going to be R1 plus R2. Right, kind of straightforward. Now let's consider Z21. Z21, we're going to say it's going to be V2 over I1, given that I2 is 0. So now if we apply a source here, I'm using different colors for the sake of clarity. Now what we do is we say, let's remove this source. Again, we can only excite one of these at the same time. Otherwise, how will we determine what's the result of what? Minus V2 here. And we're going to say that I2 is 0. There's no current here, right? There's no current over here. So what do we end up seeing? We just see current going like this. So all we see is R2, right? Z21, we apply V2, and we're going to see whatever I1 is here. Again, no current there, so just R2. And then we apply that equation now, V2 over V1. It's going to be R2 over R1 plus R2. You see this is just a voltage divider, right? So V2 is going to be V1 times R2 for R1 plus R2, exactly what we get here. But to do so, we have to have two different scenarios. Excitation here, figure out this current. Second scenario, excitation here, figure out that current. That's for very simple voltage dividers. You can see that to figure out the gain, we have to do at least 2 calculations. And for more complicated networks, it gets even harder. So is there an easier way? This is just for one of these 2 ports. Let's say hypothetically, I'm going to go over here. Let's say you got a scenario that looks like this. We want to put 2 of these together. Let's say we have 2 voltage dividers, right, for some reason. How would we go about figuring out gain from here to here? Okay. So we call this 2 port 1 and 2 port 2. Just say we have a V1. And plus minus V2. And now the math gets more complicated, as you can kind of see, because we have to figure out the gain from here to here, and then from here to here. And if these networks are complicated, that gets super tedious. Is there a better way of representing these 2 ports that'll allow us to do a simple mathematical relationship? Ideally, we want straight multiplication. We can't just do multiplication over here. We have to go through do a whole derivation. So what we end up doing is we make another representation of this 2 port. Before we said, I erased it, I'll rewrite it here. 2v1 equal to Z matrix times I2 and I1. I guess I should flip these just for the sake of notation. So 2 to 1, and that's a 2. And you see that Z has to be a 2 by 2 matrix. Oh God. Z has to be a 2 by 2 matrix for that to hold. So what we're going to do is we're going to transition to something called CVCD matrices, or transmission matrices, aka transmission. As the name suggests, it's going to allow us to easily consider a signal going from here to here. And what we do, and just for the sake of getting the groundwork laid out, this is kind of what we're going to do. this is just some ABCD matrix of 2 port 1, and we can just have direct matrix multiplication here. Matrix 2, and yeah. Actually, I guess from here I should put this I2. Right. No, wait. Wait. Put it right down here. Oh. No, wait. There. Right. Okay, this makes sense. It's like, wait, hold on. Okay, yeah. So that's how that is. And now we can just figure out these matrices. All we have to do is multiply 2 by 2 matrices, and we're good to go. And so yeah, all we have to do now is we can figure out what these things are. It's fairly straightforward. How do we figure out what these are? Well, what we could say is that for a general, we just have one of these, right? We want to figure out how this relates voltage and current. So from this relationship here, we can just say that V1 is going to be V2 minus VI2, and I1 is going to be equal to CV2 minus DI2. And we can see that we don't just have like, you know, V and V or I and I. We have V and I. And what that's effectively doing is kind of considering the power at each port versus the voltage at each port. So that way we can have a better understanding of our signal, because we care about power, right? Of how our signal is changing. Because signal is not just voltage or current, it's both. So that's a bit of intuition behind why this is better than that representation for the purpose of cascading blocks. The next representation we're going to talk about is called S parameters. We're going to go into a bit of detail, and this is where it gets a little trickier with understanding. S parameters are used a lot in RF and microwave, and it's kind of hard to wrap your head around that. Okay, S parameters, and let's start this off by saying, let's just say we have a super long, line. So we have like a power grid. We have some pole over here, bad at drawing, whatever this thing is, a little transformer, a long cable, and we have someone's house or something, I don't know. Okay, it's a great drawing. Say we send out a signal here, that's a cosine omega naught t, a simple cosine, right? And of course, things don't travel instantaneously. It takes some amount of time to get here. That time is dictated by the speed this can go at. It's going to be an electromagnetic wave propagating through this, so it's going to be the speed of light. You can just assume that to be c. And it has to go across a certain distance of line here. All right, call that L. There's a speed of c. So we expect there to be some time delay between when we send this and when the house gets this signal, right? And what we can effectively say is that this cosine, let's call this omega t, that at this house we're going to see cosine of omega t minus L over c. Right, this is like your phase shift. Omega times this is your phase shift. This makes sense, right? L is your distance, c is your speed, so we're going to get some away. And now we can say that we can define phi. It's going to be, I get L over c. And we do some algebra here. Say this is 2 pi L over the wavelength. And we care about L over the wavelength. So write this over here. If L over the wavelength is like greater than 0.01 or like 0.1, this phase delay becomes noticeable. And the idea is, okay, this is really small, this is going to be small, which means you pretty much receive your signal instantaneously. This is larger than this, you'd have a noticeable delay. This is an arbitrary 0.01, we just picked that. But the idea is things don't travel infinitely fast, it's gonna be some delay. We have some way of quantifying it, and now next question is why do we care about this delay? So if you took 101A, you'll kind of see where I might be going with this with an explicit covering of transmission lines. Like, I give you a really large scale example, it's maybe like 10 kilometers or something, right? Why do we care about this? We're not doing things at 10 kilometers. If we shrink this down, right, this to the size of like, our PCBs are maybe half the size of this, right? We can kind of start to see that our L becomes a lot smaller, which means that this wavelength doesn't need to be as like, as large to have an impact. So what that means is we shrink everything down, which means that if we start to go into like higher frequencies for a smaller distance, it becomes more noticeable, right? So for RAP, we're at 27 megahertz, and our boards are half the size of this. Do we care about transmission line effects? 27 megahertz, something this size? Absolutely not. For gigahertz things, sure. But for RAP, we don't. So why am I even bringing this up? Why am I bringing this up to begin with if we don't care about it for RAP? Because in microwave theory, when we talk about S parameters, and I'll get to this soon, we care about transmission lines. And when we have transmission lines, that's assuming that things have reflection and transmission. If you have like normal voltage divider, you're not gonna have reflection of a signal. But if you have something here super long, if things are not matched, 50 ohms for example, you'll have reflection. So that's kind of what we're gonna build up to. And S parameters are based on this notion of reflection. So despite us not really having reflections at 27 megahertz, we can still utilize S parameters, and I'll walk you through why that's still valid. Because that's something that wasn't really explicitly explained or mentioned, at least in a lot of books that cover S parameters, and it's something that I was going through this lecture and I was like, I kind of always took that for granted, so I was, let me look into why, because some of you guys might be confused as to why, and it's actually kind of interesting. So, the first point is once transmission line effects are noticeable, reflections can occur. So any incident signal on a transmission line to port can have some of its power reflected back to its source. So ideally, we don't want any reflected power, right? We want all of it to go through. That's best case scenario. It's not always possible, all right? So the problem is now if we apply some signal here, some of it goes through, some of it will continue going through, maybe a smaller amount, some of it gets reflected back, okay? We can do conservation of energy and kind of figure out, you know, how these should add up to that, right? Energy is conserved. Is there a way to quantify how much is reflected compared to how much goes through? And that's where S parameters come in. So, what we say is, say we have some 2-port here. And I'm going to, I guess, assume you guys have had 101A in this regard. Characteristic impedance is not 50 ohms. If you've not taken 101A or you're unfamiliar or you don't remember, basic idea is, if you remember from like, I guess, ECE 10, that if things are not, they don't have the same resistance and not conjugate matched, you're not gonna have maximum power transfer. You can think of it like that if you'd like. Same kind of concept applies. So we just want things to be 50 ohms, and if this is not 50 ohms, that means it's not matched. So we can think of it like that. Let's see. So, the other kind of confusing thing I'm going to draw here is the way these signals are represented. Before, we were like, oh, these bottom two are ground and our signal's up there. What we're going to say for S parameters now is one of these terminals is for forward waves, and through the other terminal is how our signal gets reflected. So we're going to just say signal goes in one way, and there's an explicit terminal that it comes out through, just for the sake of displaying what's happening. So I'm going to call this VF1, right? Some signal going in, and whatever gets reflected is VR1. And similarly, call this VF2, whatever's coming out, VR2. So if we apply, some V1 here, that's going to be connected here, it's going to result in some VF1 going in and some being returned, some VR1. That's kind of the representation we have of the system. And now I'm going to throw a bit of, matrix stuff at you. So we can say now, we can make a matrix here, VR1, VR2, S1, S12, S21, S22, just like how we had our Z11, Z12, so forth. This is going to be multiplied by VF1, VF2. Okay, just the same matrix stuff as from before. But now we're going to talk about how we get these quantities. So Si, comma J is going to be V1 minus over, it's be Vi minus over Vj plus and the plus and minus just mean the plus is like your forward and the minus is whatever's reflected. So the minus Vi minus, if I is 1, that's going to be V1 minus, which is the same thing as VR1. So the pluses and the F's are the same, the minus and the R's are the same. Actually, I could just, does that kind of make sense? This is kind of confusing. I'll give you a more concrete example. This, you have an IJ and a K, right? What does that even mean? Okay. Let's go through an example. Let's say we want to figure out S21. We care about this. This is the most important thing, S21. If you ever have an RF thing, interview or something, this is what you should remember, S21. So, I'm going to put that up here. So, I is 2, J is 1 from this, right? That's good. And this is going to be equal to V1 minus over V2 plus, okay, given, and now here's the thing, J is 1. We're assuming this is a 2-port, so that means that J can either be 1 or 2. So if J is already 1, K cannot be equal to 1, right, because J is a 1 over here. That means K has to be 2, right? So now we say V2 plus is 0, right? And this makes sense, right? We want to figure out how much is being reflected and transmitted. V1 minus is this. V2 plus is whatever we're going to see here, right? Oh, wait, hold on, sorry. Wait, hold on, I think I flipped these, yeah. Wait, the signs don't line up. Okay, sorry, hold on. This would be V2 minus, and then V1 plus, there you go, okay. Right.
Is it S1, 2?
No, it's S21. S21, yeah. Yes, yeah, yeah. So, sorry, okay, let me go back and explain this after that typo. What this is saying is V2 minus is this one, whatever's coming out from this side. V1 plus is whatever's over here. So, what they're saying is we put in a signal over here, like this V1 here, okay? We're at port 2, we're going to see something coming out from port 2, and we're going to see something being reflected. That's what we call our S21. And this is assuming we don't have a voltage source here to make sure VF2 is 0. Just like over here before, we can't put voltage sources in at the same time because we don't know what to do to what, we can see this is kind of the same thing. We have excitation due to V1 plus, which is your VF1, right? And we don't have anything in V2 plus. So this is kind of anonymous. This is the same thing as before when we can only excite from one side at a time. Slightly different notation, but you get the idea. Okay. Any questions on that? Go. So, next step, and this is where it gets a little tricky. This part, you don't have to understand in the slightest. It's a more nuanced detail about things. But, you know, at 27 megahertz, we use S parameters to determine the gain of our filters, right? I do the filter before. But I already said, hey, at 27 megahertz, we don't have the phase delays, which means we don't have like a transmission line effect, which means nothing is physically reflected. But we still use S parameters. Why? Right? And the way you can think about this is, if nothing's being reflected, can we still morph that understanding and fit our needs? And we can. It is a little hand wavy, but we can think of it like this. If this is our network analyzer, no, that's not that good. This is our network analyzer. Why are these all dead? Okay, here's the black one. This is our network analyzer. Over here, this is our filter. And ideally this has like a 50 ohm termination here, and this should also look like 50 ohms, right? I'm gonna look at this, and we just hook these up, right? What ends up happening is, if we have any, let me backtrack. Before, for transmission lines, we have reflections if things are not impedance matched. Right? If this is 50, and over here is also 50, no reflections, right? That's understandable. Over there, if things are mismatched, we don't have reflections, okay? But if this, as long as everything here is matched, no reflections. Now, over here, 27 megahertz, no reflections, what gives, right? And what we're going to do is, over here, notice that we define S parameters as a ratio of voltages. Okay, keep that in mind. Voltage ratios. When we use our network analyzer, and it's going to spit out its S21 and S11, that's in terms of dB. This is not voltage dB. This is power dB. So that's one reason. Okay. When we typically talk about S parameters in terms of dB, it's referring to power. When we talk about them in linear, it refers to voltage. It's a bit weird of a notion. Normally you'd stick to one or the other, but that's typically how it is. The other thing is that this network analyzer does internal calibration, right? If it has, let's say, it's not going to be accurate numbers, but let's say this is 5 watts here. It's going to output some 5-watt signal. If this is truly 50 ohms and this is truly 50 ohms, 2.5 watts is going to get delivered into our filter. Everyone kind of follow that? Mm-hmm. Now what's going to happen, and there's a few textbooks that use this abstraction as well. What's going to happen is we can think of this as, we have some power here, some power here. This power is half of that power. So where does the other half go? So we can think about this as this, again, another like little voltage divider. So this is 50, this is 50. We have a lot of power here, big, this is our, I'm just gonna call it a power source. That doesn't really exist, but it's for the sake of, labeling this. That's 5 watts, and we have 2.5 watts here. The other 2.5 has to be dropped here across this resistor, right? This is kind of akin to, hey, this is what goes into our system, and that 2.5 watts is reflected back. Now, is it physically reflected? No, but it is dissipated. And what you can imagine is, okay, if in a real life system, a real life transmission line, these are matched, no reflection means no power goes back. But here we're just going to say this is our match condition. If this is our match condition, we still have 2.5 watts going back. That's a discrepancy. What Nano VNA does is it says, okay, I'm going to always expect 2.5 watts back, half of my input power. And it's going to calibrate itself for that. So it's going to make 2.5 watts normalize down to 0. And that way any other discrepancies it gets, so this is like 50, or this is like 75, or this is like 1, whatever power back is going to be different than 2.5. And then it's going to compare that 2.5 to its reference of its new 0, and compare that value and figure out where it is. Yeah.
Just kind of taking like maximum power,
Yeah.
and comparing maximum power to whatever it gets.
Yeah. Because when it's matched, it expects 2.5 watts to go back into itself. If it's unmatched, we're not going to get 2.5 watts. So what it does is basically just level shifts everything. You can think of it like that. That way, we actually use our Nano VNA for the filter, and we look at our S11 and our S22. We can actually say, hey, if it's matched, we expect, like, I can draw out the curve here. So we have a 5 megahertz filter, 5 megahertz. We expect our S11 something like this, our bandpass. Let's just say this is negative 20 dB, right? Nano VNA is dB. This is a power quantity then. dB for S parameters, power. Negative 20 dB means that pretty much no power is being reflected back. This is 1/100th of our power is being reflected back, right? 99% of it goes through. But in reality, 2.5 watts goes back, half of it. So it does a level shift with the power here, basically, and calibrates it in reference to 2.5.
But like 2.5 isn't actually the, so how does it measure that?
It has an internal receiver inside of it. That's where it gets complicated. But it has a separate receive path inside of it. It has one receiver here, it has receiver 1, it has a receiver A, and it can do calibration. But that's way beyond this. But that's the idea, is that, yeah, as much as we don't have reflections, we can abstract it away by just saying whatever's reflected is dissipated, normalize it out. And that way, this is still accurate. It's just a way for us to still measure matching and kind of gain, without really needing to have super high frequency things, because otherwise, we're not always going to measure high frequency things. So that's how this works. So hopefully, it's not too confusing. So then when we actually use reflections in rap? This, we would think reflections, but now it's subtracted away. This, okay, cool, reflections, but like I said, for 27 megahertz, what do we do? And this is where it gets interesting. Transistors, we can think about as a 2-port. 3 terminals, but you can just make, your emitter ground, and that way I'll draw it up. But what we're going to do is say transistors are a 2-port themselves, right? And that's kind of what we did before, the small signal model, right? We made a 2-port. So let's do that. So this is where it's going to get a little tricky, and all the math is going to come out. So if you don't get it, don't worry about it too much. This is like a 2-port for a transistor, right, for a BJT. The emitter is the common terminal here, your base and your collector, right? We can agree that we can model this as a 2-port somehow, in some shape or form. What we're going to say now is, what we're going to say now is we have some source impedance, ZS, just like how you do Nano VNA is at 50 ohm. And we have some VS here. And going to do, so we have some ZL here. And this is where it gets kind of complicated. Do you guys remember the reflection coefficient from 1.1a? It characterizes, it's kind of how S parameters are. There's a relationship between S parameters and reflection coefficient. We're going to write some reflection coefficients out because we're going to assume these are not matched, right? And that means signals can reflect. Okay. Again, are we talking about actual reflection here? Not yet. We will get to that. But for now, what we're going to do is we're going to try and model a transistor with S parameters. And that'll be hopefully made clear 20 minutes from now as to why we do that. So, this is going to be our source reflection coefficient. This is going to be our gamma in. And this is going to be our gamma L. And this is going to be our, I'm gonna call it gamma out. I did, yeah. Gamma out. Okay, this makes sense, right? Source, a load, these have its own impedances looking at this way and that way, so they have their own reflection coefficients when we normalize to 50 ohms. Right? Cool. So what ends up happening? This is where it gets a little tricky. Okay. When we made amplifiers before, you know, we had BJT, I'll draw it out. BJT, I'm gonna ignore the biasing network for now. Resistor, this is our V out, this is our, it's here, this is grounded, goes RC, assuming it's biased forward active region, small enough signal, the gain is negative GM, RC parallel, R naught, right? And what you guys talked about in the last module was, okay, replace this with an inductor, and that's a capacitor, can resonate, get rid of this RC, so we just get negative GM, R naught. And we're like, okay, that's a good way of maximizing it, maximizing our gain. However, we still end up having, we think about that, right? We're gonna have, what we did before, we said, okay, there's gonna be an inductor here, and there's gonna be a capacitor, and then that's our BJT. This has some R naught. So it's ground, so voltage source, our input. I was like, oh, okay, our gain is gonna be negative GM R naught, assuming this resonates with this and looks like an open. In reality, this is gonna have some parasitic resistance. So RS. So our gain now is still negative GM R naught in parallel with some resistance. It's not RC anymore, it's RS. So this is kind of troublesome. Sure, we get the benefits of slightly higher gain from this, but there's still this. So it's not our maximum gain available. What we want to do is say we pick a random transistor. We use the MMBTH10. Get as much gain as we can out of it, which means we really need to understand how this thing looks. If we understand what this thing looks like, we can put it into another network and squeeze as much performance as we can out of it. The other interesting thing here is in RF we care about power. A lot of other types of design we care about either current or voltage. And I'll get into those nuances later in the lecture, but for now, keep that in mind is everything we're doing here is to build up this idea of squeezing as much performance as we can out of these transistors. So I'll leave this up and I think I'll erase something here. By the way, all these concepts, S parameters, you really only touch on in 163A officially. No one really teaches it to you apart from that, and even then it's kind of like, you just have to read a textbook. It's a really good textbook. It's called, if you guys are interested, I'll write it up here. It's called POSAR, Microwave Engineering. SP Split Engineering? Yeah, okay, cool. Yeah, POSAR is Microwave Engineering. Is that correct?
Yeah.
Yeah? Is it? Yeah, okay, it looks, okay, I think it's fine. Yeah. Microwave Engineering.
The handwriting is writing is.
Thank you. I mean,
hiding all the mistakes.
this is an R. This is an N. There you go.
Okay.
Yeah. Microwave Engineering. The book's in the lab if you guys want to take a look at it. Really cool book. It's like the Bible for RF engineers, pretty much.
And I heard the class is a relaxed class.
Yeah, it's a cool class. You learn a lot. It's one of my favorite classes. But it's one of those like you really have to just put in time and read the book to get as much as you can out of it. Otherwise, it's not going to do much for you. Because it's really dense content. Like you'll see next 5 minutes or so the equations I'm going to pull out, and you're like, this is really overwhelming. But you'll see why. So, okay, we want to squeeze out as much gain as we can out of this transistor, so we want to define gain somehow. If we know what parameters gain consists of, then we can try to maximize it, right? If we have no idea what gain is related to, then how can we even start to, optimize? So, there's a few types of gain that's denoted in the book. I'm gonna talk about one specifically, the rest aren't as important. It's called transducer gain. G of T. And I'm gonna define this as, by the way, this is all in reference to this drawing here. The power delivered to the load over the power that's available from the source. The power available to the source from the source is whatever power makes it here. Okay? Because you can have any amount of power here, but if none of it makes it here, then obviously none of your power is going to be delivered to your load. So we care whatever power is delivered to your load from here, given power here. That way we can figure out directly this is the gain, right? Power here, power there. The gain of this is this power divided by that power. Care about power quantities, not voltage quantities, like we did here. Okay? That's one distinction that's very important, is power. And we'll see why soon enough. I'm going to throw more math at you guys. So, what we can see from here, the power right here is dependent on ZS. It's depending on our matching here. Similarly, whatever power we see here and here depends on whatever the ZL is. Right? This means our gain is dependent on whatever our input circuit is and whatever our output circuit looks like. Right? Which is kind of a weird concept to wrap your head around. It kind of makes sense. Right? Go back over here. So this gain is ZS, ZL dependent. Have an equation for this gain. It's going to be quite a lot. It's the magnitude of your S21 squared times 1 minus the magnitude of your source reflection coefficient squared over 1 minus S11 times source reflection coefficient, all that magnitude squared times this. This is your transducer gain. Kind of intimidating. The magnitudes just refer to the fact that these can be complex, right? Your reflection coefficients, and for all of them, and then obviously your S21 can also, yeah.
What's the difference between S11 and the source reflectance?
What do you mean, like, so, okay, yeah. So your source reflectance is your S11 effectively.
So why is this not S11 squared?
Where?
Down.
This?
The lower one. Left.
This?
Yeah.
What do you mean?
Why is it not 1 minus, like S11 squared or like?
Oh,
Gamma.
okay. Yeah, you have to, I don't have the math here. If you want, actually, you have to lecture the whole derivation. This is me skipping like 2 pages of derivations in the book.
Okay.
Yeah, I just want to give you guys the
Thank you.
equations and we can derive meaning from it.
Oh.
Yeah, because the math's quite a lot. It's quite a lot. I've never actually gone through I've gone through the math myself, but it's never been like, that 163A class, there's a reason why it's all open note, open book.
What kind of classes?
163A. Yeah.
I think I almost, that class only has like 25 people or something.
Yeah, at least when like Ramji and David and I took it, it was all grad students. Yeah.
I almost took it, because I almost didn't get to
Yeah.
48.
So this is definitely advanced content I'm throwing at you. Like, don't get it wrong. This is, no interviewer's gonna ask you this, but the concepts are what's important. Concepts that, hey, gain depend on ZL, ZS. What's an S parameter? We talked about that, right? Stuff like that.
So is
Yeah.
there a difference between gamma of S and S sub 11?
Yes, they are related, but we're just choosing to have them as separate terms. Yeah, there is a relationship between them. Yeah, this is just easier representation. Okay. Now let's say we have perfect matching here and here. Okay, everything's 50 ohms. Perfect matching. what happens to our transistor gain? All right. Ideally, we want that thing to be as high as possible, right? So if everything is matched, I think I'm doing really good on time too. My concern was I wouldn't be able to show you guys an ADS example after this. This simplifies S21 squared. This is really nice. Now you remember before when I talked about S parameters, S21 is a voltage quantity. And we are squaring it. Squaring voltage and we are getting like a power gain. That thing's kind of weird. What's happening is the assumption is everything's terminated in 50 ohms. Right? If I have it's 50, this is 50, call this V2, call this V1. The power delivered to V2 is going to be the power that is seen here divided by 2, right? Because effectively the voltage is split. The current is the same, the voltage gets halved, right? So the power at the load we're going to end up doing is going to say it's V1 squared over 2R, where both of these are R equals 50. Right? This is normal. This is different than your normal V1 squared over R from power. You have the voltage divider here. So if we're saying, hey, everything is you know power related. Sorry, let me take a step back. S21 is a voltage quantity, right? And you can see we have it's a voltage quantity squared. So you can see the sum relationship there, and then there's this 2R, right? What's effectively happening is that this is gain, right? This is going to be some power. PL over like PS, right? If everything is 50 ohms, the PS here, this is also going to see a 50 ohm thing here, in which case the PS is also going to have some VS squared over 2R, right? You can see the 2R's cancel out, and now we just have the ratio of 2 voltages squared. This is the ratio of 1 voltage squared, right? So you could say V1 over Vs, all that squared. And you can see how it kind of relates back to our S parameter being a ratio of voltages. Now these numbers may not be exact because you know we have a reflection. Just for the sake of example, that's how the units work out. In case anyone is confused, because we go from dB to voltage to power, and it's not explicit which one you use when you use S parameters. It's something that through experience you'll kind of realize what they're talking about. And there's no exact like thing, it's just convention. It's very annoying. But hopefully this explains it to you, because I never had anyone explain that to me. It's something that I was, again, looking through today when I was trying to figure out what questions would you guys have. I was like, wait, I never actually thought about the units like that. Let me see if I can explain it. So this is, I think it works well enough to explain that phenomenon. Yeah.
So the V1 over Vs, that's a unitless quantity, right?
Yes.
But the S parameter has a unit, no?
Well, this is gain. So the assumption is it's unitless, right?
Oh,
Even if you
okay.
put something in dB, it's all relative, right?
Right, okay.
Yeah. When we talk about like, when we reference it in terms of power, it's like a relative to power, right? Talking about power referencing, but it's not units of power. Is the thing. Yeah. Okay, so I'm gonna erase this, but this is the important part. S21 squared, if we are matched. So you can write a conclusion from this, and that is the power gain of the transistor I'm gonna write transistor because this holds for any transistor, not just BJTs. Heavily dependent. The impedances presented to it. How do we characterize the impedance is presented to the transistor, S parameters. So now you can see how it's kind of coming together. We have a transistor, we know its gain, we've got to figure out what we hook it up to, what those impedances are, find the S parameters of those two networks, and we can put it all together. Okay. Let's see. Okay, I think this is a good place to take a 5-minute break. It's a good segue. Yeah. Okay, any questions so far? Cool. Big takeaway. Transistors have a certain amount of gain. They have a maximum gain rating by the manufacturer. They present a certain impedance at all terminals. We choose to represent the transistor instead of a Z matrix with S parameters because it makes all of this math easier. Okay, S parameters are a tool, is the idea here. It's what I would like to get across, is that they help us formulate easy ways of messing around with this transistor and hooking it up to different things and getting meaningful insight out of it. Because if we use Z parameters, that equation wouldn't be as clean. Alright, we wouldn't just get this. We wouldn't just get the S21 squared. So it's kind of a clean result. Any questions so far? We can take a 5-minute break. Cool. You got that video? Fine.
No.
Same. Alright, okay. The whole point of this, one, design amplifiers. And the common meme or joke, I should say not meme, the common joke in analog and RF design is you try and make an amplifier, you make an oscillator, you try and make an oscillator, you make an amplifier. You can't get it to oscillate. You make an amplifier and maybe some feedback or something, and you end up making it the feedback too strong, you get an oscillator. Or sorry, too weak, you get an oscillator. So how do we avoid that? Can we even get an oscillator out of this? Like, we look at this and it's like, there's no path from the output back to the input. Like, let's use a different color here, sorry. When we talk about Colpitt's oscillators, we're like, oh, there's a feedback path here, so then we can get oscillation, right? But there's no feedback path here. All right, so how can we get oscillation? And this is, again, where S parameters come in handy. So I'm gonna go back to that side and draw it out. And hopefully this is like really cool for you guys. I mean, I hope it's cool. It makes the math a lot harder, but it's interesting to be aware of this. So, abstract away your source network. Some reflection coefficient. Same as we did over there. And we have some 2-port again that has BJT inside of it. So, like this. And obviously we're excluding biasing, right? But whatever. And we have a load network. Gamma L. Okay, now this is where I'm going to draw a lot of lines, and it happens in a certain order. Okay, so I'm going to try using different colors, but just try and keep track of what happens. Because things kind of go back and forth. Okay, let's say right here. Say we have some signal coming out from the source. Okay. It's going to go over here. Down. Cool. We have signal here. Goes way over there into our BJT. Some of it is going to go through, become our S21. Some of it gets reflected here. Okay. The thing that gets reflected, this part that gets reflected, is going to hit the source network. And it's going to get reflected back. So maybe a smaller portion. This is your S11. Whatever gets reflected back is going to be your S11 times gamma S. Okay. That's one thing. Whatever gets initially transmitted goes over here to the output, our BJT network, and hits the load. It hits the load, by the way, the top parts I'm using as forward, bottom patch reverse, right? So it gets reflected, it's going to become S21 times gamma L. We're good there? Okay. So, what happens now? S21 times gamma L is going to go back over here. Okay, it's going to hit our source. Sorry. We go back over here. This gets reflected and ends up going back into our device, our dot. Whatever goes in, just like how whatever signal goes over here gets multiplied by S21, right? This is going to get multiplied and show up in this different color over here as S12 times S21 times gamma L. Does that make sense? Okay. Now this is going to hit the source and reflect back. And what's going to happen now is S12, S21 gamma L. I'm trying to use a parentheses to establish the fact that this is already present and this is the new thing. This is already present, this is the new thing. Right? So now we see, okay, over here we get gamma S, S12, S21, gamma L going back into our device, the S1 gamma S from before. And this whole cycle repeats over and over and over, infinitely. Are we good with that? Any questions? So, what we can do is keep writing out these terms. So that means what we're trying to find out is just the total signal that ends up here, right? We want to find this total signal, that total input signal, okay? So from there, what we're going to say, this initial gamma S, S11, plus this term, gamma S, S12, S21, gamma L. I'm going to erase this now. Plus S22 gamma L, yeah, times this quantity. This goes on infinitely. And you can see that this S22 gamma L is because this ends up going back here, gets reflected by gamma L, and goes back. So the S22 part comes into play there. Yeah. So this goes on infinitely. And if we want, we could factor out a gamma S and gamma S term from everything. And if we do a Taylor expansion of this whole thing, we can see that this is equivalent, this infinite sum, equivalent to gamma S times S11 plus S12, S11, gamma L over 1 minus S22, gamma L. Okay. And this is what we're going to denote as, I wrote it down over there, gamma in. Same gamma in as this. But you can see that these infinite reflections, signals bouncing back and forth, going from source to dot to load, back and forth. Infinite sum, we do a Taylor expansion, look at this.
How does that Taylor expansion work? Like, what are we
Great.
taking the derivative with respect to?
Oh, no, there's no derivative.
I just mean,
Sorry,
you
not a
think
Taylor.
Taylor
it's-
expansion
it's
is matching
an-
derivatives.
Yeah, what I'm referring to like, like 1 over 1 minus
Oh, the
x.
geometric
Yeah, yeah,
series.
yeah,
yeah,
the
okay,
power
okay,
scheme,
yeah. Getting the exact one used for this. I mean, you can maybe look this up as well.
Actually do remember that.
Figure it out. It's hard, a little hard to see, but you can kind of see how it comes together.
I swear we did like something like this in something similar to this
Yeah.
came up in 101A where like
Probably in
It's
101B, I think, too, they talked about. Because I remember this problem showing, well, this showing up with like antennas in 101B.
yeah, with the antennas, not
Yeah.
with the BJT, but yeah.
Yeah, it's the same concept though, right? instead of BJT, you'd have air as your medium or some dielectric. Okay, so this is your gamma in. It's what we wanted to find here, right? So we found gamma in. Can we find gamma out? Well, we can just, if you want, we can redo this whole thing, or by symmetry, out is going to be equal to L times S2 plus S21 S2 gamma S over 1 minus S11 gamma S. Cool. Okay. Now, let's talk about how does this lead to this notion of oscillation? Well, oscillation, how should I write this? I'm gonna erase this problem right here. We need that diagram up there. Oscillation is possible if either the input or output port impedance is less than 0. This makes sense. We talked about oscillation before. We were like negative resistance, right? So it's like less than 0, negative. That tracks so far. Any questions on that? I kind of expect something to be less than 0 here for oscillation. So this kind of lines up. Next thing is, what does this imply? And this means, let me see if I have written this out somewhere. Thought I did. Okay, hold on. Here it is. Okay. So generally speaking, we have some gamma x. Zx minus Z naught over Zx plus Z naught. Okay, if this magnitude is going to be greater than 1, right? If this magnitude is greater than 1, then what's going to happen is that, let's see, what do I have it here? 1 second. Yeah, this magnitude is going to be greater than 1. And what we're going to see is that it has to have a negative impedance, right? This magnitude is greater than 1 because this is always going to be larger, this denominator, than the top, right? C naught is 50, this is like 60, then we get 10 over 110, right? If Zx has like a negative component, right? Negative, negative, and then that becomes a negative at the top. So say it's like negative 60, so we get negative 110 over negative 10, right? Okay, well that's a bad example. Basically, the magnitude can go above 1 if this is a negative component, which you can kind of see, right? Because you'll get like a larger negative number, but the magnitude of a large negative number can be greater than 1. Right? So for this to be greater than 1, the magnitude, this has to be negative, which means that oscillation occurs if this is greater than 1. So oscillation occurs if gamma in or gamma out, the magnitude is greater than 1. Gamma in and gamma out depend on gamma S and gamma L, right? Gamma S over here, gamma L, gamma S. This means that our stability, what determines if we oscillate, is determined by gamma S and gamma L. Gamma S and gamma L, well, it's how well we are matched between this and our dot, our UJT. So we can see that sometimes here we can get the oscillation just by plugging something in. So we get like reflections and everything, right? So that's something to be aware of. So based on how this matching is, if we don't match correctly, we can get oscillation. Next step is we don't want it to oscillate, we want to make an amplifier. How do we avoid that? For that we're gonna write a few terms out, a few definitions to help analyze that. So one term is called unconditional stability. This means it's gonna be stable. Yeah, what's up? Thomas.
How much longer in the lecture?
35 minutes, 40?
Okay, thank you.
Why?
Thank you. Sanjay wants to know.
Oh. Okay, cool. What a wood. Okay. Where was I? Okay. Unconditional stability. We are unconditionally stable, which means we're not going to oscillate no matter what. If magnitude gamma in is less than 1 and magnitude gamma out is less than 1 for all passive sources in mode. What this means is ZL could be a 1 ohm resistor, it could be 1 mega ohm, ZS could be 1 ohm, 50 ohms, whatever. No matter what ZS and ZL are, as long as they are passive, and these are held for any of these, any passive elements, we're not going to be oscillating. So if we can get to this stage where ZL and ZS don't affect our stability, that's good, right? So, this is where it gets trickier. Can we try and, we have a lot of variables here, right? Assume that, when we have a certain BJT, the manufacturer gives us the S parameter file, so we know S11, S22, S12, S21. That helps with some of those equations there. But we still have two unknowns, gamma L and gamma S, right? How do we figure those out? Those are based on whatever ZS and ZL are. And we're saying for all passive networks. So are we going to sit there and do the math for an infinite number of possibilities? Exactly, we are. No. We have a tool that we use, the good old Smith chart, to help us determine how stable we are. Because if you remember on the Smith chart, we normalize to a certain Z naught, right? If we have an impedance of 0 divided by 50, that's 0. If we have infinity, it still goes to infinity. So the Smith chart can kind of encompass all these infinite options we have. Alright, you can kind of see where we might be going with this. I'm going to try and draw a Smith chart as well as I can, but I have an example on my laptop as well I can pop open and show you guys. That might be a bit neater. I'm going to do this back here. And what we're going to do is we're going to say, hey, let's say we're right at the boundary of stability. Let's say our gamma in is exactly equal to 1, because worst case is one of our gamma ins or gamma outs is equal to 1. That's the boundary between instability and stability, right? Over here. As long as these are less than 1. But if it's 1, that's the boundary. So we can figure out where that boundary is. Then we either know if we are inside that boundary, we're going to be stable, or outside, we're going to be stable, but splits it up into two options, two kind of realms. So visually, if we can draw some boundary out, then it helps us visualize what's happening. Okay? That's just kind of the intuition as to why, worst case, it's helpful to be aware of where our boundary is. Splits the plane into two. So I'm going to call a term here called the stability circle. And the stability circle is the circle for which we say gamma n is equal to 1. And I'm going to write it all out. But first I'm going to define a few parameters. define delta as S11, S22 minus S12, S21. This is the determinant of our S parameter matrix. This is a variable we're going to use. If we have this variable, then what we're going to say is hold on one sec. Let me think here for a second. Let's see. Right, okay, yeah. Okay, so if this is 1, right, what we can do is move some terms around with algebra, maybe do some cross multiplication, blah, blah, blah. We'll do some cross multiplication, get it into some algebraic form, and then we're gonna plug this term in there. Okay, I'm not gonna show all the math, how we get there. I'm just gonna show a final result, and what's gonna happen is we're gonna have two quantities, like x equals y, that's gonna stem from this. All that's saying is we set this equal to 1, we cross multiply, and then we plug delta in and get this x equals y relationship. So don't worry too much about that derivation. Just know that whatever equation I'm gonna write comes from this, okay? So with this variable in mind, we get this. Okay, this is equal to basically, we just get inequality here, and here's what we're gonna do. This is right at the boundary of oscillation here, okay? And what I'm going to do now is, in the complex gamma plane, okay, we might go 10 minutes over. Equations of the form gamma minus some value equal to r. This denotes a circle centered at C with radius r. So this might look something like this. This is C. It's imaginary. This is real. Okay. Basically, what this is telling us is that along this circle, no matter where we are, gamma in is 1. This means that we have two distinct regions. This could be stable, this could be a stable region, this could be it, but right now all we know is there's two regions out. So we can plot this circle, and then we can figure out which is stable, and we know where we can be to make it unconditionally stable. Okay, so don't be confused by this. I'm skipping a little bit of derivations there, but hopefully that makes sense. And we call this a low circle here, because we're saying gamma in equals 0, and if we say gamma out equals 0, then we have a source circle, and at another point C with a radius r. Different C, different r probably, but same concept applies. If you want to see an example of this, there's a page on Posar, page 586. If I have time, I'll show it to you guys, but if we don't, then you can look at that. But is there an easier method of, actually I will show you guys an example. Do that now. I think we have time. I think that'll be kind of insightful. That example will tell you whether the inside or outside of the circle is stable, without me getting into all the math. I don't remember all the math. While that's happening, my laptop's opening up, we'll get back to the circle thing. There has to be an easier way to figure this out, right? So plotting a circle, going to Smith chart, doing all that work, why even bother, right? Is there an easier way? And turns out there is. It's a much easier way of doing so. It's called the K delta test. And the idea behind this is let's abstract away all these terms into, two variables, K and delta. And how big these K and delta terms are, it'll tell us how stable we are. Okay. So we have unconditional stability. If K, which we define as 1 minus magnitude S11 squared minus S22 squared delta squared, all of this over 2 magnitude S12 S21, this is greater than 1, where magnitude of our determinant is less than 1. And this means that if this is true, then the conclusion we get is that S11, magnitude of S11, S22, less than 1, which we kind of hope, right? We don't want reflection. And this is great if K is greater than 1 and the determinant is less than 1, we get unconditional stability. Let's say we have two circuits and both say, oh, K is greater than 1. One might be closer to instability than the other. So we want some way of now figuring out which ones are more stable. So for this, we, instead of using K, we have some other parameters we use. We have a mu S, a mu L term. So this allows us to do relative split. So mu S, we're going to say is going to be 1 minus S11 squared over S22 delta S11 plus magnitude S12 S21. And then for mu L, it's the opposite, because source and load kind of flip the ones and twos. And if both of these are greater than 1, we are stable. Now all we have to do is just say, hey, let's plot these, see if they're stable, and we're good to go. So, what now? What do we do? Go back. Yeah, I can erase this now. We're nearly at the end of this. So, I'll give you guys a few examples here. And this is what you can see on ADS. This is what you'll be plotting if you want to do the amplifier design. US, UL, and I'll give you guys a template. You don't have to import any of these functions, right? It's already a part of the software. You just have to click simulate whatever circuit you make. So this is 1. So that one axis is like this. It's like mu S. Or mu L is something like this. Right? We are only unconditionally stable in this region. This means if we go outside, because this goes below 1, we have a chance of being unstable. So what we want to do is ideally have both of these curves be above 1 for all frequencies. So what we're going to see is we have a transistor, we want to operate at 27 megahertz. 27 megahertz might be in here, maybe at 1 gigahertz or over here, and it's below 1. Okay, you may think, okay, we operate 27 megahertz, it won't be an issue. But let's say we have, really strong 1 gigahertz signal from some, I don't know, say David's doing something, right? 1 gigahertz signal, and our antenna can't, attenuate that completely. There's going to be some power left through, and some of that 1 gigahertz signal will come through, and it can hit our system, hit, that BJT, and if we're unstable, there's potential for exhaustion. So we want to make sure that we're unconditionally stable because we can't rely on something being attenuated to 0, right? You can never fully reduce the signal without, as I talked before, like I think in the first lecture, if we have a filter that looks like this, 1 and 0, which we can't do because we can't have infinite cost or infinite number of inductors and capacitors. So we want to make sure we are unconditionally stable no matter what. Because if we're unstable, then we're unstable. Okay. Now let's just say, I'll give you guys another example here, beyond just this. Let's say we have mu L is less than 1, and I'll draw a Smith chart here. Oh, that's not good. Okay. Pretend this is a well-drawn Smith chart. Okay. This is our Smith chart, and this is our point C. This is our R, and that's our like stability circle, right? The thing we talked about over there. And let's just say, although I'm not showing you guys this example yet, let's just say that we are stable if we are within this region here. Right? If we go in here, we're unstable, potentially. So wherever here, we're good. We're good to go. So right now, we are right over here. We're at the boundary. All right, and we want to get mu L greater than 1. Okay, and let's just say this point is at 200 ohms. Okay, so what do we want to do to get mu L higher, right? What we do is we say, okay, we want to go in here. In the Smith chart, as you go further out, our impedance gets higher, right? Because we normalized to 50. So 1's over here, right? If we want to go this way, we want to bring our impedance down from 200, right? So what do? Let's see, I'm going to erase this part. And this is very relevant to if you design things. Let's say you have like your amplifier here, right? Say BJT, and then, it looks like 200 ohms, right? So what do? Is we do this. This way, 200 ohms in parallel with anything is always less than 200 ohms, right? Which means no matter what, we're going to be here. So before, it was just like this. You had the ZL. And 200 ohms was the value at which, for ZL, that's the boundary point. We put 200 ohms at ZL, no matter what ZL is, we're now less than 200, right? So that's a neat little trick. We can put something in parallel. So we go back to our amplifiers from before. Maybe we had something that looks like this. DC blocking cap, this is ground, you have the biasing network, blah, 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 whatever, right? Now, this is like our load, our 50 ohms. Say that's the antenna. If this is the antenna, shove a 200 ohm resistor here. Now we're stable. We're good to go. So we did all that math just to come to, hey, this, you want less, put a 200 ohm resistor in there. That's the basis for all of this. And actually, let me just skip this up here. Demonstration purposes. So now let me talk about actual amplifier design process. We did all of this just to say things can be unstable. We want to maximize gain. Remember we got that transducer equation, that magnitude of S21. It turns out that, I don't think I mentioned this explicitly. There's an example in the book as well. But S21 squared is not the highest point of that transducer function. This is kind of weird because that transducer function simplified itself to S21 squared when we were matched. This means that there is a point at which we are unmatched that gives us the highest gain possible. That's a bit weird to think about. We would expect highest gain when we are matched. But because of the way we have modeled our networks with these S parameters, with these reflections, the key takeaway is if we're not matched at 50 ohms, we can potentially have a maximum somewhere else. Meaning that if everything's 50 ohms, we'll get some gain, but it might not be the max. And if we want the max, we have to find that out somehow, what that max is, where is it, what source and load networks it requires, and match to that instead, not 50 ohms. And I may line up that the max gain is at 50 ohms, depending what values you have. But generally speaking, that may not always be true. That's the important takeaway you should get from this. So we can't just match things. You have to be careful of how much gain can you squeeze out. And ADS will tell you the maximum gain you have. You make some circuit like this, you make some circuit like this, it'll tell you the maximum gain. It'll say, hey, first make sure you're stable, then it'll tell you what your maximum gain is. It's going to tell you what source and load networks you need to insert, and you'll insert a load network here. You'll insert the source network here between your 50 ohm source, this is your source here, to make sure a maximum gain is achieved. The design process is as follows. We're going to, first we know we pick up a transistor from the market. Hopefully the manufacturer provides us the S parameter data, or we look through the data sheet and figure out what it should be. Okay. And then we try to make our classic common emitters. The first step, ensure unconditional stability. Because what we saw from over here is it's 200 ohm resistor, right? Where it was before over here, right? Or just gonna put it here too. All right. What this does is it changes the biasing of our transistor. You have S parameters given a certain biasing, right? But if you change the biasing, your S parameters change. So what ends up happening is, yeah, sure, this 200 brings us in here, but how does this 200 show up here? How does it make UL higher? Because it changes your S parameters. That's the important part. So you change whatever your transistor sees. That's going to change the biasing. So we change these S parameters, and hopefully that change is enough to make your MUL 1. Okay. So your S parameters change. And what you typically want to do is if your system is close to, if it's going to be like this, right, you want to insert loss. Whatever this oscillation is, if that's happening, that could potentially happen, because you have too much reflection back. To do so, to degenerate a signal, you make it lossy, you put loss in the path. Well, this looks like a resistor, right? If we insert a resistor here, it's going to degrade our output impedance. It's going to make some signal go this way, some go that way. Not all of it goes here anymore. So it introduces loss. And generally speaking, if we have something like this, we want to insert loss in these frequencies to bring this up. Typically, if it's like this, maybe you want a resistor, it'll bring all of it up. In the smaller region, we'll do different things. That's the idea. Insert loss somehow. Next step is to maximize power transfer. You have to follow a few things. And now this is where we do conjugate matching. I erased it, but you gotta remember that our source and load networks, those are gonna be all the way at 50 ohms. You put things in between to make sure you see 50 and then the other thing that then sees your BJT. That other impedance is where your transducer function will be at maximum. That's not gonna be a 50 though, typically. So the other cool thing is there's no trade-off here between unconditional stability and max gain. If something's unconditionally stable, you can still extract the maximum gain from it. Typically, you expect it to be a design trade-off. Hey, we make it stable, but don't get as much gain. No, we can still get the max gain. So that's something to be aware of. I mean, there's a little approximation made there, in reality, no. But for BJTs, yeah. For transistors that have a low S12, you could do it. That are unilateral, you could do it. So we can still max for maximum gain. And usually software can do all this for us, which is really nice. We don't have to do any of this math, we don't have to do any of these circuits. We build this thing, we click simulate. It's going to tell us, it's going to plot this curve. It's going to plot our gain circles, which tell us, depending on what frequency we're at, what the gain looks like, and then we can take it from there. So, one last thing I'd like to touch on, and then I'll show you guys an ADS example, is does any of the things we've talked about so far contradict what we've learned in the past? Before we were like, okay, we have our gain for any network as GM times R out, negative GM times R out. But now we're saying that over here before we thought, okay, if we just make R out super large, get a large gain. One thing to note here first thing, this is a voltage gain. We're talking about power gain. That's already kind of one discrepancy. The next thing is, in all the circuits we talked about before, GM and Rout had no common variables. In other words, Rout is a function. So that Rout is like a function of RC, it's a function of R naught, it could have been a function of RE. For the inductor, it could have been like RS. And of course RL, right? GM, we saw typically, is this going to be a function, just lowercase gm, alright? But what if this big GM also had some relationship with RC? So yeah, we can make RC larger, get a larger R out, but what if this has the opposite relationship? RC goes up, R out goes up, RC goes up, big GM goes down, these two kind of cancel out and their voltage gain stays the same. We didn't see that before, but now because we take into account S parameters and the reflections, we can see that we can't just simply make, you know, one of these parameters super large. There's going to be some interplay between them. Because we can't just assume these to be independent functions. And that leaves it. Let's see. Any questions? I know it's a beefier, very beefy lecture, but I hope you guys have obtained something from this. I want to show you guys one thing in ADS very quickly because I want to get you guys ADS licenses, and there's no mandatory like module or anything. This is like the point in rap that we're at right now is able to make it for the weekend work session great. It's gonna be assembling things. That's cool, but what's the most beneficial thing you can do to further your understanding is messing around with ADS. So I want to show you guys what ADS looks like, how it kind of takes all the concepts we talked about and, you know, realizes it in a kind of intuitive manner. So let's see. Yeah, you can stop recording, I guess, because it's gonna be hard to record my screen and